Okay, so you've got your assignment due today or tomorrow, or Saturday, I guess, depending on how many late days you take. Any questions or problems about that or anything else? Yes?
It asks me for the depth of a branch on comparing depths on a tree.
Which problem asks about the depth of the tree?
I believe it's in PS2.
Second last question in the second. PS2 is due.
So PS2 asks for the depth of a branch on a tree. Okay.
Right.
After rotating it.
Okay. What's the question then?
So if I go from, let's say I have a node, I go from root to 1 on the left, is that just depth 1 or is that depth 0 for it?
It'd be depth 1.
And then if it has like child to the right and then 2 children, that's still just depth 2 on either child. So, okay.
Yes.
Perfect.
Number of branches you go over to get to the end. Any other questions? Yes?
Can you clarify on the hash table one? It says the hash function just returns a random integer less than the number of buckets every time. And if you don't find it, you rehash and just keep going until you do find it.
Okay, I'm going to look at that because I want to make sure I answer that correctly. That's how it's worded. Which problem was that?
PS2, the second part, and then it's question 10.
Okay, so it's just a hash function that's a random number generator. Okay, you call the hash function, you get back a random number.
But then if you don't find what you're looking for in that bucket, you rehash.
Now, the hash table works just like before. It's just the hash function. The hash table works just like any hash table. The hash function returns a random number.
But then is this also talking about worst case of insertion or finding?
I'm just saying which is the worst. Yeah?
The hash function generates each time is called and returns a random integer k, or 0 less than the number of buckets. I assumed that random integer was generated repeatedly such that it would be the same each time the hash function was called on the same object. Or were
No.
a random integer...
It's just a random number. It takes a random number, integer, mod k, and returns it. Every time you call it.
Do you have a specific seed for random number generator or anything like that?
No, it's a random number generator. It returns a random number, believe it or not. Okay? You call it twice, you get a different number probably. It ignores the thing it is hashing. It returns a random number. Any other questions? Okay, we were talking last time about the master theorem at the end. So let's continue there. So what you should recall is that if you put the, if you have a recurrence relation of that form, T of n equals A T of n over B plus O of n to D, that gives, where the recurrence gives the running time or the space consumption or whatever of some method, then you can put a big O bound on that function T by using the master theorem. So let's just think of a couple of cases and analyze them. What about binary search? Just plain regular binary search, not the strange one I dreamed up last time. So for binary search, what would be the constants A, B, and D? for binary search. Yep.
It would be 1,
Okay, tell us why A is 1.
because we're just splitting it once.
Okay, you split the array in half and you make a recursive call. We're doing the worst case here. You do one recursive call, either the left half or the right half. Only one recursive call is made, so that's A. What's B? Someone said 2, so why is it 2? Yep,
Splitting out the sides.
right, we're splitting things into halves. So basically, we're multiplying, the sizes in at one level recursion, it's 1/2 in on the other, at the other. So really take the reciprocal, the factor is 1/2, but we divide them by it, so we take the reciprocal. Anyway, it's 2. And then, what about the D for binary search? Where does D come from? Yeah?
Would it be the comparison to see if we found the number?
Okay, so it's what the D gets to the work that you do exclusive of the recursive call. So what do you do before you make a recursive call in binary search?
Here.
You do a comparison and then decide which way to go. So that takes constant time. And then what do you do after you get your answer back from the recursive call? You just return it yourself, right? So that's constant time. So if you ignore the cost of the recursive call, the other work in binary search is constant time. So what does that say about D? It's 0. Because what we're looking for is, we're trying to put a bound on the work of the form O of n to the D. In this case, it's constant, so D is 0. N to the 0 is 1. So it's O of 1. Okay? Once you've done that bit of analysis, it's easy to apply the master theorem. So in this case, in each case, we've got to compare D, which is 0, to log base B of A, which would be log base 2 of 1. So to what power do you raise 2 to get 1? 0. So what do we have? Which case are we in now? We got D is 0 and log base B of A is 0. So which of these 3 cases are we in? Okay, we're in the second case. So the answer is O of n to the D log n. So O of n to the 0 log n, which is just O of log n, which is what you'd expect. Yeah?
I'm a little confused about the D. If it's constant time, then why isn't it 1?
Well, okay, if we make D 1, then we're saying the work exclusive of recursion is O of n. Okay? Which is true, but it's more precise to say it's O of 1.
Okay, so when we were looking for constant time, we want the O of something to be constant time.
Yeah, if constant time is O of 1, you're trying to put the tightest bound you can. Tightest polynomial bound you can on the extra time, on the other time. And yeah, we could say it's O of n squared. It's true, right? It's an upper bound. What if we did say, okay, the extra time, we're really sloppy, and we say the extra time binary search does, exclusive of the recursion, is O of n squared. What answer would we get if we use the master theorem then? O of n squared would be in the first case. Is that true? Yeah. It's an upper bound. But the better bound you can put, the smaller you can make D, the better answer you're going to get out, the tighter bound you're going to get out. And the smallest we can make D is 0. Okay? Let's think of another one. What about a situation, let's take Mergesort. Suppose that we decide, splitting the array in half and doing merge sort's good. Maybe splitting it into thirds would be better. What if we did a merge sort that split the array into thirds, sorted each piece, and then did a 3-way merge? Okay, let's think about that. So what would the A be in this case?
3.
Okay, we're splitting it into 3 pieces. Okay, and what would the B be? All right, each is a third. And, well, we have to decide 3-way merge. I can imagine doing a 3-way merge in linear time. You just look at 3 elements instead of 2 and figure out which is the smallest. So that's constant time. So that means, I mean, not constant time, linear time. So what's D? 1. So which case are we in? Okay, let's do log base 3 of 3, which is what? 1. And D is 1, so in the second case, our answer is O of n log n. So without having to work very hard, we can see that a 3-way binary search is going to have the same order of complexity as the regular, I mean not binary search, merge sort is going to have the same complexity as regular merge. Yeah?
So when we split it in halves, why was A 1, but in this case when we did it in thirds, A was 3 exactly? Like why wouldn't it be like 2 or something?
Okay, A is the number of recursive calls you make.
Oh, okay.
So for binary search, we split it in half, but we only did a recursive call for one of the halves. So we did 1 call, each half the size of the original. Here we're doing 3 calls, each a third the size of the original. Yeah?
And then just on the D, why is it 1? Why is it linear this time? You're just comparing 3, isn't that just basically constant?
Well, think about what we're doing when we do a merge. If you're doing a 3-way merge, we've got an array that's been sorted, an array that's been sorted, an array that's been sorted. Yeah, you compare the first 3 elements and pick the smallest, but you're not done. You've got to process all of the arrays. You know, eventually you've got to copy all of these elements into another array.
Okay.
By comparing 3 at a time, copying the smallest 3 at a time.
So the key is not to think about it in the lower levels of the recursion, but just the...
Right. All you do is, you don't worry about the whole recursion tree. The master theorem was derived by worrying about the entire recursion tree. But the beauty of it is, you don't have to worry that it's recursive at all, except you've got to identify the recursive calls. You take your method, like merge sort, you figure out A and B from the recursions, and then how do you figure out D? You've got your code for merge sort. How do you figure out D? What algorithm analysis do you do?
You look at everything that's not a recursive.
Right. You basically ignore, cross out the recursive calls and just do a regular algorithm analysis on what's left. There's no recursion at all to consider in getting D. Okay. What about, let me think of one here. How about a strange algorithm that it makes 2 recursive calls, each half the size of the original, and it does a log n amount of work, exclusive of the recursion. So imagine it's like merge sort, except it does the merge takes log n time. It's not a merge, but it just takes log n time to do what it needs to do. So what would A and B be? 2 and 2. And what would D be? Well, D can't be log of n. D has to be some number. Yeah?
How did you say group, or how did you say, what was the runtime that you said for the...
So what I'm saying is that the amount of work that you do exclusive of the recursive call is log n.
How would you do 0?
Well, we got to say log n is O of n to some power.
Oh, well, for the second case of n to the d times log n.
Well, we're not there yet. We haven't figured out D.
Oh, gotcha, sorry.
Yeah.
You do log n over the natural log of n?
No, I can't have logs. I've got to figure out an exponent here such that log n is O of n to that exponent, if I want to use the master theorem. Yeah?
1.
Okay, I can certainly say that log n is O of n to the 1. Do you all agree? Got a question? You got an improvement?
I was just wondering, does that have to be an integer?
No, no, and we'll look at that in a second. Okay, so if we do that, D is 1, and we do the analysis, what do we get? Okay, log base 2 of 2 is 1. D and that log are the same as in the second case, and our answer would be O of n log n, just like merge sort. Which doesn't seem quite right because we're doing something that's a lot easier than merge sort. So that end of the 1 bound is too loose. We can tighten that bound on log n. What would be a better bound we could put? What's a tighter exponent we could use than 1? Yeah?
Do you use log base n of log of n as an exponent?
No. No, it has to be, we need a constant. Yeah?
Any number less than 1.
Some number less than 1. Any number, any positive number, into any positive power is going to grow faster than log. So why don't we just say it's 1/2, just for, see what happens. Okay, that's still a true statement, right? Log of n is O of n to the 1/2. But what case does that put us in now? If d is 1/2. Now we're in the third case, and then what's our overall complexity? O of n. So again, we got a better answer because we put a tighter bound on this. So this extra work won't always be a nice polynomial for you. It may involve logs. And if it does, you put, it doesn't have to be an integral bound into some power. You need to have, ideally, you put the lowest possible exponent there that'll work. Now, what if we used 1/4 or 1/8 or 1/1,000,000th? Would it change our answer? We're still in case 3 where d doesn't matter the final answer. So by making it a little bit smaller than 1, we were able to get a tighter bound. Yeah?
Can you define the difference between A and B again?
Between which?
The difference between A and B.
Okay. A is the number of recursive calls that are made. So you just look at the code, and you see that it always makes 2 recursive calls. That's the A. The B is the amount by which the size of the input decreases. So if it goes down by a factor of 2, then B is 2. Yeah?
So how would you know, like, to choose, like, 1 for D? Like, when you're trying to find what the exponent should be, if you know, like, the work is log, that we're trying to get log n?
Well, how would you know to choose D here, to choose this exponent here?
Yeah.
We want it to be as small as possible. Right? We want the tightest possible bound on the extra work. Now, if the extra work is n squared, then clearly the smallest we can make D is 2. But if the extra work is log n, we could make n be 1 or 1/2 or 1/4, anything as long as it's positive. But it turns out that as long as we use something smaller than 1, we're okay. In this case, because we get to the third case where D doesn't matter. Okay, let's think about this in a different way. Okay, so there's our master theorem. Now I just want to remind you I didn't show you where the master theorem came from, but I'll remind you of the work that we did before. We took copying binary search, and here we considered the entire recursion tree. We figured out if you looked at the entire recursion tree, how much work was done at the top level, how much at the second level, how much at the third level, how much in the base cases, added it all up, and got our bound that way. But if you use the master theorem for copying binary search, what were the values for A, B, and D we would get? How many recursive calls are made? 1. So A is 1. What's B? 2. We're dividing in half. And what's D? What's the amount of work we do? That was linear amount of work at each level because I just threw in a gratuitous copy. So D is 1. And so it turns out that copying binary search is a situation where D is greater than log B of A. D is 1, log B of A is 0. No. Yeah. Log B is, yeah. Okay. So we're in that situation. And in copying binary search, we found that The top level alone in copying binary search was the entire O of n. Once you did the top level, the rest of the stuff doesn't add up to as much as the top level. And that turns out to be characteristic of a situation where D is greater than log B of A. And when you're in that case of the master theorem, what's the answer? It's O of n to the D. So basically the master theorem is saying when you get this kind of recurrence, all that matters is the amount of work you do at the top level. Right? That's where that case comes from. Okay? Merge sort. What were the A? Again, we added up everything. What's the A, the B, the D? I already did this. What's A? A is 2, B is 2, D is 1 for the end of the one merge. So that's a situation where D is equal to log A. And in this case, every level contributes equally to the complexity. That's what we found. We were doing a linear amount of work on each level, and there were log n levels. And the master theorem in this case would say the answer is n log n. So when D and log B of A are tied, the answer is n to the D log n. The n to the D is the amount of work at each level. The log n is the number of levels. So that's where that case comes from. And then finally, we looked at recursive multiplication. In this case, A was what? 4. We turned one multiplication into 4. Each one was half as big, right? So B is 2. And what was D? What did we have to do when we multiplied? We split our number into 4 other numbers, did the multiplications. What was the work of recombining them to get the overall answer? It wasn't n squared. We had to do some bit shifting and some adding to reconstruct the number. What's it take to add n-bit numbers? What's the complexity of that? Yes, linear. So there D was 1. So we had here D was less than log BA. In this situation, it was the base cases that dominated. And so the answer is O of n to the log BA, where that's a measure of the number of base cases there are. So the 3 examples that I chose to analyze in detail illustrated the three different cases of the master theorem. Now, if you want to prove the master theorem, which I don't propose to do, what you would do is you would just consider a general case recurrence. You do what we did for those 3 specific cases. You would just say, okay, you start with 1, and then at the next level you have A recursive calls, each of size 1/8 of the original, and you would laboriously calculate the amount of work at each level, the number of base cases there are, add them all up. Then you end up with this sum right there you have to work out. And it turns out if you want to compute that sum, you have to use 3 tricks depending on whether log BA of less than D, log BA is equal to D, or log B of A is greater than D. And then by making one of those assumptions, it's possible to do the sum. So that's just a sketch of the proof of the master theorem. It's just, we sort of did it for the 3 cases. I picked 3 special cases that illustrates each of these. And we did it using constants, actual numbers instead of A and B. But in principle, we could do the same thing here. It's just a matter of figuring out the infinite sum, not the infinite sum, the sum you've got to calculate and calculating it. But that would take a long time to actually work through all the details. It doesn't really help us probably understand the master theorem. I'm just after, there's the master theorem. You've got some idea where it came from. And I want you to be able to use it at this level here of just taking divide and conquer algorithms and figuring out their complexity. Yeah?
So, is it hard to tell the difference between an algorithm that's divide and conquer and one that's not?
Okay, he's asking, is it hard to tell the difference between an algorithm that's divide and conquer and one that's not? So let me put that out to you. What does it mean to say an algorithm is divide and conquer? Yeah?
Well, at least in the context of this theorem, it would have to be dividing this, like this workspace into equal parts.
Okay? So it does that. It takes a problem and divides it into two or more subproblems, or let's just say one or more subproblems, each the same size. Resolves those problems recursively, and then when it gets the answers back, it recombines them into an overall answer. That's divide and conquer. All right, well, recursive multiplication turned out to be a disappointment because it has the same complexity as grade school multiplication. But let's not give up just yet. We're going to look at a variable called Summa multiplication. So, we're going to multiply x and y, and we'll assume they're n bits long. So we've got two n-bit numbers, x and y, we've got to multiply. And just like we did for the recursive multiplication algorithm, we're going to split x and y into halves. So xl will be the first half, the first n over 2 bits. xr will be the last n over 2 bits, and the same for y. So we've got 4 numbers now. So just like in the recursive multiplication algorithm, I'm going to compute xl times yl. And just like before, I'm going to compute xr times yr. Now, in the recursive multiplication algorithm, we did 2 more multiplications. What were they? 2 more recursive multiplications. Yeah? Right, we cross multiply xl by yr and xr by yl. And that was 4 multiplications, and we do the recursive multiplications, and then we had a way of by bit shifting and adding to compute the final answer, but it was not an improvement over grade school. We're going to do something different. This was the key idea that Summa had. This is the 3rd multiplication we're going to compute. We're going to add xl and xr. We're going to add yl and yr and multiply them. And you might be looking at that saying, what the heck? How does it make any sense to add the 2 halves of x and to add the 2 halves of y? Okay? And this is how you get your name on an algorithm. You have that idea. So let's expand that out. All right? That's just the thing expanded out. Now, can anyone look at that and tell me, how can we get from there to where we need to be? I don't want to do any more multiplications. Yeah?
Subtract P1 and P2 from P3?
Right. What would happen if I subtracted P1 and P2 from P3? I already got P1, I got P2. If I subtract P1, I get rid of this term. If I subtract P2, I get rid of the last term. And what's left? XLYR, which is one of the cross multiple pairs we needed, and XRYL, the other one. So I've got there, and here are the 4 products I used in the recursive multiplication algorithm. What's the only difference? Do I really have XLYR when I do this? I have 3 numbers, right? When I do the subtraction, see what the next thing is. So I have this difference, which is XLYR plus XRYL, plus I have P1 and P2. But I have the sum of these 2 things, not them individually. In the recursive multiplication algorithm, I have this by itself, and this by itself, and those 2 things by themselves. Here I've only got the sum of these 2 things. Now, is that a problem? That I only have the sum of XLYR and XRYL instead of have the numbers individually. What do you think? Is that enough information? Does anyone remember what we did with this product and that product in the recursive multiplication algorithm? After we made the recursive calls and got the answer back for these 2 products, what did we do with those 2 products? Anyone take a guess if you don't remember? Yeah, we added them. All we need is the sum of those 2 things to do the multiplication. If you go back and look at the recursive multiplication algorithm, you'll see One of the first things we did after we computed the product was to add these together. So we don't need to compute them separately and then add them. We just compute their sum directly. So once you've got those three numbers, that's how you do the reconstruction. You take P1, bit shifted by n bits. You take that sum of the two inner terms, bit shifted by n over 2 bits, and then you add the bit shifted P1, the bit shifted sum, and the bit shifted P2, and you got your product. So is this going to be faster? What's the trade-off here? We only do 3 recursive calls now instead of 4. But is there we're doing extra work here, right? We're having to subtract P1 and P2 from P3. And we're having to add XL and XR and YL and YR. So there's lots of additional additions and subtractions we're having to do we didn't have to do before. So is that worth it? To get rid of one recursive call, but we're adding a number of additions and subtractions at each level of recursion, mind you. Yeah?
Yes, since addition is just going to be constant time.
No, the additions aren't constant time. Remember, we're working with arbitrary length integers. So how much do the additions cost? They're linear. They depend on the number of bits. Same for the subtractions, same for the bit shifts. So is it worth it to make the work that you have to do before and after the recursion more complicated if you can reduce the number of recursions? Yeah?
Well, you're like adding more n, but it's still going to be n.
Right. So what he's observed is, yes, we're doing more additions and subtractions, but still the overall work is linear. There are more linear time operations we're doing, but that's still linear. But we're eliminating a recursive call, and that's huge. You're eliminating a recursive call at each level of the tree. So let's see how much better we did here. Okay, so what's A here? Recursive multiplication. How many, we take in two numbers of length n. How many recursive multiplications do we do? 3. Okay? What's our B here? 2, because each number is half the length that it was before. And what's the work that we do setting up and recovering from the recursion, which is additions, subtractions, bit shifts. That's linear, so it's D is equal to 1. So what's the log base 2? What happened here? What's the log base 2 of 3? I don't know what it is, but it's greater than 1. So we're in the case where log base B of A is greater than D. So what's the answer in that case? O of n to the D. So it's O of n to the log base 2 of 3. How does that compare to O of n squared? It's better. Log base 2 of 3 is less than 2. So it's an improvement. So if we go back to the slide, no, that's not the slide. Did I kill the screen? I think I killed it. Okay, so we get back here. Look, it's O of n to the log base 2 of 3, which is O of n to the 1.59. So we've gone from O of n squared to O of to 1.59. Okay, that's an improvement. You might think, well, that's not a big deal, but in fact it is for large enough values at n. Yeah.
How do you know what tell there are 3 recursive calls?
How do you know there are 3 recursive calls?
Yeah.
Okay, this is a multiplication algorithm. So how many multiplications are we doing here? 3. So those dots are the recursive calls. We recursively compute P1, we recursively compute P2, we recursively compute P3. Those are the 3 recursive calls. Before we do the recursive calls, we have to do a couple of additions. Then we make the recursive calls, we get 3 products back. Then, when we get the answer back, well, before the recursive, then we have to do a couple of subtractions, and a couple of additions, and a couple of bit shifts. Yeah? Say again a little louder.
Can we give an example of this algorithm?
An example of this algorithm?
I'm just having a hard time seeing how that actually computes.
Sure, since you asked, let's do an example. I'm not going to do it in base 2 though. I'll do it in base 10. Same trick works. All right, let's multiply 25 and 18. Okay? So what we do is we split our number up into 2 and 5, and we split our numbers up into 1 and 8. Okay, so these are the x's, these are the y's. What do we... Make this a little bigger. So what do we do? What are the products we compute? Yeah? Okay, so we got to compute 2 times 1, and we get 2. We compute 5 times 8, we get 40. What's the other product that we compute? Okay, we add the 2 and the 8, and we add the 1 and the 5, multiply them. So 2 and 8 is 10. 1 plus 5, wait. Yeah, 2 and 8 is 10. 1 plus 5 is 6, so we get 60. If you see me make a mistake, let me know, because I haven't practiced this. Great. So we've got, this is our P1, P2, P3. So let me stop there and see if there are any questions about how I got this far. Yeah?
So I thought you were supposed to add the left side and the right side of the x's. And the left
You're right.
side and the right side of the
Thank you.
y's.
That's why I told you to tell me if I made any mistakes. I'm glad you did that, or it would have been a complete disaster. Okay, we need to add these guys. See, it just doesn't make any sense to add the same things together, right? But we're adding 2 and 5, so it's 7 times 9, right? That's 63. Very good. So far, so good? Now, what do we do when we get the answer back? So we got our products. What do we do with them? Right, so we want to compute P1, we're going to subtract off P3 minus P1 minus P2. So that's 63 minus 42, which is what? Is that 21? 63 minus is 21. Okay, so now we have the 3 products. We have that, we have that, we have that. And our answer is just going to be P1 times 10 to the first power, because we had 2 digits, plus, what was it that P3 minus P2 times P1, no, this is 10 to the 2, this is times 10 to the 1. This is plus P3. If I'm remembering the formula correctly. Because in the original formula, I'm just making sure I got those exponents right. It was, I think it was 2 to the n there. It was 2 to the n over 2 there. Am I remembering that correctly?
Yeah. Far right side is P2
Plus P2, okay. Okay, now is it correct? Yeah?
The reason we're not considering the P1 times 10 to the second recursive call is because that's just bit shifting?
That's just, well, in this case, digit shifting, yeah. Right. So that's a good question. We don't make a recursive call to this multiplication because we just have to basically stick 2 zeros on the end. That's just a digit shift. If you're working in base 2, it'd be a bit shift. That just takes linear time. All right. What is the answer, by the way? Did anyone calculate it already? 25 times 18? Is it 450? Okay, let's hope we get 450. So P1 times 10 to the second is going to be 200, right? And this next thing times 10 is going to be 210. And what's P2 going to be? 40. Wow. Okay. Of course, I made at least, what, 2 or 3 mistakes along the way. But thanks to your guidance, we got to the end and we get 450. Now, I don't know if that illuminates the algorithm or not. It just seems like magic in a way that it works. Yeah.
This has more space complexity than the other algorithms.
What do you mean, more space complexity?
Like, I mean, it has more, it has recursive calls, and at each one there's lots of variables. And this one
Okay.
makes more space.
So you're saying there are more temporary variables needed?
Yeah.
Yeah. But it's still, at each level of recursion, it's a constant number of temporary variables. So it's still, the depth of recursion is governed by the log of the number. Well, let's try to get some other idea of how much better this is than grade school. What happens if you take two numbers and multiply, two n-bit numbers and multiply them using grade school algorithm or the recursive multiplication algorithm, and then that takes a certain amount of time? What's the doubling behavior? What if you double the number of bits in the numbers you multiply? Make them twice as long. Not twice as, you're not multiplying by 2, you're actually doubling the number of bits or the number of digits. What will happen to the running time? We know that in n-squared algorithm, doubling behavior says it's going to be a factor of 4. And just to remind you where that comes from, is you say, okay, the time it takes to deal with number of size n is n squared. The time it takes to deal with number twice as long is going to be 2n squared, and that's 4. Okay, what's going to be the doubling behavior of Summa multiplication? How would we compute it? Yeah?
It would be like 2n to the power of 1.59 over n to the power of 1.
Right, so it would be n, I'm going to actually, instead of doing the simplification, I'm going to say log base 2 of 3. And this is the time for something twice as big. Okay? Now, 2n to some power is equal to 2 to that power times n to that power. So that means we can divide out the n log 2 of 3. There's one of those terms at both the top and the bottom. So what are we left with when we do the division? 2 to the log base 2 of 3. And remember, if your rate exponentiation by 2 is the inverse of log by 2. So they just cancel out and we're just left with 3. So that's the doubling behavior of Summa. You double the length of the numbers, the running time triples instead of quadrupling. And that can make a big difference. Now, you might be wondering, how long do numbers have to be before it makes a difference? We'll talk about that probably next time. But is it important to be able to multiply arbitrarily long integers? Is this even a practical thing, or is this just pure theoretical interest? Why would you need to do exact multiplication? Not about floating point numbers. Exact multiplications for arbitrarily long integers. Yeah?
Encryption?
Encryption is the #1 example. Encryption, you're using numbers of, like 2,000 bits, say, which is going to be hundreds of digits. And techniques like this are used. It turns out that there are even faster ways to multiply. So I looked once at the Free Software Foundation's big integer package, written in C, and I think they had 4 different approaches in there. So they had grade school, if numbers are really small, they use grade school multiplication. A little bit bigger, they use Summa. Then you get into techniques that use fast Fourier transforms. And they become, the extra complexity becomes valuable as the numbers get longer and longer. Okay? So today so far we've talked about a couple of things. We've got more practice with the master theorem. And we've seen here how Recursive Multiplication works. You won't find that name in the book. For some reason, they don't credit Recursive with this in your book. I like to give credit. This was invented in the 60s. And then I think it was just pure theoretical interest. Okay, let's take a break and we'll look at some more examples. What I want to do is just give you some practice designing divide and conquer algorithms. So here's the first one I want you to work on. You're given a sorted array of distinct integers, so there are no duplicates, and it's sorted. Determine whether there is an index such that a sub I contains I, and do it in logarithmic time. So, for example, this array right here. Does it have an index where a sub I is equal to I?
4?
Yeah.
Yeah, so 0, 1, 2, 3, 4. So the answer is yes. But what's wrong with the way I just did it? That would be linear time if I'm just going to go through and say, yeah. No, yeah. In some cases I have to get all the way to the end. So that doesn't fly. And so what we need is a divide and conquer algorithm. Now, the fact that it's a logarithmic requirement, what does that imply? Something like a binary search. If the complexity is log n, that means you cannot look at all the elements. Your algorithm cannot possibly look at all the elements, where it'll take too long. So you've got to think in terms of dividing it in half and then going from there. So try to adapt binary search to this purpose. And you got a question or an answer? Yeah, I don't want an answer just yet. So take a few minutes, talk to the people around you, and come up not just with an algorithm, but a justification for why it works.
Alrighty, Bruce, what's your strategy?
Binary search.
Okay.
Keep in mind,
Yeah, Bobby.
Let's see. We'll put it on the intermission.
Don't screw with it, Bobby.
okay, who could tell me an approach here? Yeah.
So you can start in the middle.
Start in the middle, let's say, I don't know,
0.
say 0. Well,
and
that's,
then,
okay.
And then you check if it equals I.
Okay, so the index is 0, 1, 2, that would be index 3.
Yeah.
Okay,
And
so you compare the 3 to the 0, it's not the same. So how do you know which half to look at?
And then you check if the value is less than the index, and if it is.
Okay,
right.
so someone else pick it up from here. The 0 is less than the index 3. So where do we look? Yeah.
You're just going to look on the right half.
Okay, why is it not going to work to look to the left? Because, yeah, it's sorted and there are no duplicates. And so as we move to the left from here, the index gets smaller by 1 each time, right? 3, 2, 1, but the numbers are also getting smaller, at least that fast. They have to get smaller, so you'll never be able to catch up. You have 1 to the left, now you got 2, but this is, the number's going to be even smaller than 0 was, so that's not going to work. Now if there weren't integers, then we'd have hope. Or if there were duplicates, we'd have hope. But the bottom line is, we know the answer has to be over here. So you focus your attention on what's left and do what? Same thing. You probe in the middle and proceed that way. So it's a lot like binary search. The only thing that's different is what's different is the justification of why you can throw away 1/2 over another. That's not obvious at first. So there's an implementation for what it's worth. You know, we probe in the middle and then we either go left or right. And we know that's going to be log n because it's basically binary search, but just for the heck of it, let's analyze it. What's the A, the B, and the D for this divide and conquer algorithm? A is 1, B is 2 because we're splitting in half, D is 0 because constant time work, So there's our recurrence relation, and we just get log it out. Okay? All right, here's another one. You've got an array A of all the integers except 1. Between 0 and a power of 2. So essentially you might have all the numbers from 0 to 7 except one of them, or all the numbers from 0 to 15 except one of them. And your job is to find the missing one in linear time. But to make the problem interesting, it wouldn't be interesting otherwise, you're only allowed, the only thing you can do with an integer is look at individual bits. So you can go to a number and say, what's the high order bit? What's the next, what's bit 0, what's bit 1, what's bit 2? So you can look at the bits and compare bits of numbers. But you can't, and you can copy numbers, well, can you copy numbers around? I guess you can copy complete numbers. So you can't look at every bit. Not enough time to look at every bit. I'm going to do it in linear time. So figure out how to do this faster using divide and conquer. You're not starting to talk as fast as you did before. It's a little harder trying. Give it a shot. Talk about it. Who's got an idea? What can we do? How can we divide this problem up? Okay, so you can look at the bits and you can copy the integers. Yeah?
It's not a complete idea, but say we look at the first, we count all of the binary digits on the very last binary number, And so like say we have like 5 ones and 4 zeros, then we know that we can eliminate half of the options using that information. So,
Okay, yeah. So did you hear that? So imagine taking all the numbers and just look at the high order bit of each one. Count how many zeros there are and how many ones there are. And it's not, they're going to be an odd number of numbers because one's missing, right? There would be a power, it's 1 less than a power of 2. So let's say you got the numbers from 0 to 15, but 1 is missing. So the one that's missing either starts with a 1 or a 0, right? So if the one that's missing starts with a 0, you're going to end up finding 8 ones and 7 zeros when you scan. So you looked at the first bit in every number, and when you find out that there are more ones than zeros, what do you know? Say that again. Well, first of all, it means the missing number starts with what? A 0. So you know the first bit of the missing number. All right, and then how can you simplify the problem at that point? Yeah?
Check the next high order bit is only that half of the...
Okay, so you can throw half the numbers away at that point, right? All the ones that start with a 1 are in the array. It's numbers that start with 0 are missing. So throw away all the numbers that start with a 1. Now you've got, in this case, 7 numbers left that all start with a 0. Look at the second bit. Find out which is missing there. Yeah?
When you say throw it away, what do you mean by that? Like, if this array, you said it wasn't sorted, right?
Right.
So then how would you ignore those, I guess? Would you just...
You'd have to copy the numbers over.
You'd have to copy them.
Yeah.
Wouldn't that potentially be... I feel like that would be too slow, I guess.
Well, we can, I mean, it's an overhead, but we can account for that when we do the analysis. Yeah, so we're going to scan every bit. In each pass, we scan every bit of what's left. We figure out, is it a 1 bit or a 0 bit that's missing? And you concentrate on you throw away the numbers that are all there, and you concentrate on the other numbers. So there it is in words. So if k is equal to 1, there'll be a single 1-bit number. So its complement is the one that is what's missing. Otherwise, you count the bits. Like I said, you throw away part by copying the ones that you care about. So what's the complexity of this? How many recursive calls do we make? 1. Right? You're going to do a scan and figure out which half to ignore and which half to recurse on. So there's A is 1. What's B? 2. You're cutting the problem in half each time. And what's D? What's the cost exclusive of recursion each time? What's the cost of looking at every bit? That's linear. So that's O of n to look at every bit. What's the cost of copying half the numbers over to somewhere else? N over 2, but that's still linear. So what's D? 1. So we get that recurrence. 1 recursive call, each half the size of the original, plus a linear amount of work at each level. And there's our deal. And so D is greater than the log base 2 of 1, so our answer is O of n to the D, or O of n. So it's linear. This is a lot like that copying binary search that I analyzed last time. It cuts the problem in half and does a copy. In this case, the copy is necessary. So when you design a divide and conquer algorithm, what's the hard part? You know you're going to have to divide the problem into pieces. So where does the creativity come in? Yeah?
It comes in ruling out possibilities faster. Like this one, you can rule out each time you recurse, you have to rule out a certain number of possibilities that you don't have to check for or work with. Right?
You're not always ruling out possibilities. Sometimes you, in this case we did. But like in Mergesort, you saw both halves. But yeah, that's part of it, yeah?
I'm
you say it's super expensive. It's linear.
Is it just linear?
Yeah. But we do a linear number of operations. Some of them are copies and some of them are looking at bits. But it's still linear. It's proportional to the length of the array. Yeah?
This is the case where most of the work is done for class, right?
This is a case where, yeah, the work you do at the very top level ends up being the complexity, yeah. Okay, so again, think about it. What's hard about this? Yeah?
Finding a way to divide it in such a way that you can like recursively call it again, right? So like evenly dividing it, I guess is a way of putting it.
Yeah. Okay, so you're sort of getting at it. It's, I mean, there's sort of this aha moment when you're designing a divide and conquer algorithm. You got to figure out, all right, how can I split it up, and you know, what do I have to do before? What do I have to do after? It's not the recursion that makes it hard. It's that germ of an idea. Oh yeah, I can count bits. I can see, is it zeros or ones are missing? Or I can probe in the middle and throw half away. It's coming up with that creative insight that makes it tough to design divide and conquer algorithms. Or think of Recursive Multiplication. That's a really good example. It took a flash of insight to realize that you could reduce the number of multiplications you're doing from 4 to 3. That makes a huge difference. But coming up with that idea is not always easy. Okay, now here's another one, and we're going to look at 2 algorithms for this. And it's important because the caddis problem for next week, you'll be using, you're going to need to use a majority element algorithm to solve it. And let me just emphasize that. You are going to have to use an efficient majority element algorithm to solve it. You may look at it and think there's some other way you can do it, but believe me, it was designed, it was my problem. And I sat in my office with Peter Jensen for a long time to figure out a way to have a problem that you couldn't solve by other techniques. So or at least the kind of techniques I expect most students would know. So you need to pay attention to this. You really need to use it, and I'll still get questions from students saying, why is my program taking too long? It's why. If you're not using an algorithm for this problem, it's going to take too long. All right, so you're given an array of elements, and you're trying to find a majority element. A majority element is an element that appears more than half the time. So this array has a majority element because there's 1, 2, 3, 4, 5. There's 5 of them. That's more than half. This one does not because there are only 4 ones, but there are 8 elements, so that's not a majority. This has a majority element, which is 5. That one does not. Right? That's the whole game. So we can just say we're given integers. In your case, they won't be integers, but they're things that you can compare to each other in some way. And I'm ruling out hashing because and comparing. When I say that they can be tested for equality, they can't be ordered, they can't be hashed efficiently. Integers obviously can, but we'll just agree not to use those operations here. Okay? So I want a divide and conquer algorithm to solve this. And I'm going to give you a little help. I'll suggest something. I want you to split the arrays into halves, solve the problem for the halves, and then use those results to solve the original problem. So what you've got to figure out is, if you take an array and split it into halves, and solve the problem for the first half and solve the problem for the second half, what's the answer to the first subproblem going to be? It's more than yes or no. It's either going to be no, this array does not have a majority element, or it's going to be yes, it does, and here's the majority element. So you either get back a number that's the majority element, or you get back no. Okay? So you need to figure out, given the answers to both halves. Maybe this half says 5 is the majority element of this half, and you learn that the other array has no majority element. Okay? Or you may find out both have majority elements and they're the same, or maybe they're different. Or maybe neither have majority elements. There are lots of possibilities. Think about how you combine the results of the recursion. So to set up for the recursion, you split the array in half. The interesting work comes when you get the answer back. How do you combine the 2 answers to obtain an overall answer? Okay? So think about that for a few minutes. Yeah? Hi, I'm Bruce. So let's just break it down. What if you got back, you had some array and you split it, and you found out that for the first half there was no majority element, and for the second half there was no majority element. So neither half has a number that occurs more than half the time. What's the answer you need to report in that case? No. If something's going to occur more than half the time in an array, it's going to have to occur at least half the time, more than half the time in one of the arrays. Okay, so the answer here is no. What about if you find out if the answer is no, and you get back some y that occurs more than half the time? So let's look at an example here. Let's say our number is 1, 2, 3, 1, 1. And you got to split it somehow. Let's say we split it so that we got the extra thing there. So the answer would be no. The first half does not have a majority element, but the answer would be yes, the second does have a majority element, and it's 1. What do you do in that case?
Do you need to check for y in no side?
Right. What you have to do is essentially forget about the halves. Just make a pass through the array and count how many times y occurs. Okay, you see, y is the key observation here is the y may not be a majority element. it is here. How could we change this so we get the same answer, the same two answers, but such that one was not a majority element? Yeah, change that first one to a 0. The answer would still be no and 1. But one would not be a majority element in that case. So Y is the only candidate to be a majority element at this point. So the whole point of the recursive call is just to identify a possible candidate. Then you just count how many times it occurs in the array, and in this case you find out it does. Essentially you've got to count Y to give an answer. You had your hand up first.
Sorry, I was just going to ask, I didn't see any specification of the question that said how fast it needed to run.
That's right.
So are we just giving ideas of how we do it?
Well, I'm giving you, for the way I set up the problem, I believe this is the fastest that we can do.
Okay, I agree.
Yeah?
Do you have to count Y, or do you see that it occurs once?
Do I have to do what?
Count Y, or do you just see that it occurs once on the other side?
Well, we can't just count how many times, find out it occurs once. It works in this case, but we don't know how many times Y occurred on the right. Okay? So we need to, but complexity-wise, it doesn't matter if you count through half the array or the whole array. It's still linear time count. Yeah?
What happens if your array, rather than having 1, 2, 3, 1, 1, what if it's 1, 2, 3, 1, 1, 2, 2?
Okay. 1, 2, 3, 1, 1, 2, 2?
Yeah.
Okay, and we're going to split it. You want to, same, like here?
No, 1 over. No, what if you have it split 1 over left?
Okay.
Because then you get a no, no.
Okay, so we get back a no and a no. And so we report no, which is the right answer. There's not a majority element. So it takes a little bit of work to convince yourself that that case is correct. Yeah?
What if you had even sized array with like 1, 2, 1, 3, 1, 4, 1, 5, or 6?
1, 2, 1, 3, 1. Yeah, no majority element. Yeah?
So in the first example you did, if that 1 was a 2 at the beginning, so it's 2, 2, 3, 1, 1.
Right.
You would say yes on both sides. What would happen?
Okay, let's get to that. So what if it's the other way? What if it's X and no? What if we split and it says, yeah, the first half has a majority element, the second half is no? We just got to count the X's. And what if the answer is X and Y? It says, yeah, each has a majority element. Yeah? If X and Y are the same, you're good. What if they're different?
Check each other.
You need, in that case, you need to count X and count Y. Either of them could be a majority. For example, you could have this, 1, 1, 2, 2, 2. If you split it here, both have majority elements, but you can't say no, because 2 is a majority element of the whole array. You have to count the 1s and count the 2s. Yeah?
We found a problem. What if it was like 2, 3, 3, 5, you split it down the middle?
2, 3, 3, 5?
Right, you split it down the middle, both of them say no, but...
There's no majority element. It has to be more than half.
Oh, it has to be more than half. Okay, sorry.
Okay, one more question.
More like the solution.
Hmm?
You should like split it like side by like 3. You want to go like 3.
Well, okay, so I can't go on indefinitely. There's a better algorithm we can look at next time. So we'll finish this next time. If you work on the CAS problem before next time, take a look at the slides we didn't do.